number of guests arriving before time t is a Poisson process with the rate, okay, with the rate lambda, right? So, so here the tau k being distributed as an exponential, and so nt is a Poisson process, right? So now, in general, the tau k could be anything. So definition number one. So now given a sequence, I guess it's a given tau k. All right. IID taking values in the non-negative real line 0 to infinity, not including infinity. All right. Then as usual, let me denote t sub n to be the summation of 1 to n. Okay. Right. And so t is again the maximum on n, such that tn, which is summation of k1 to n, tau k less than t. Alright. So still think about nt as the number of guests arriving up to time t. But now the inter-arrival time, the tau k, is just a generic continuous random variable. It doesn't have to be an exponential, right? So nt now is, okay, so then nt is called a renewal process. To give an example, well, so the first example in this issue, in this renewal process case here is the, obviously we have the exponential where we cover the Poisson process example, right? Number one, suppose if I have tau k is first IID, exponential lambda. Then the Poisson process what nt is a renewal process. Right. Very first example that we already learned, chapter 2. Second case, a little bit more difficult to see is that Markov chain. So given a Markov chain XMN, right? With x naught, suppose I start from x. Right? So denote tau k, sorry, say tau 1 to be the first time returning to little x, right? And tau k is the length, the waiting time. So this will be k here minus dk minus 1. Right? Sorry. I forgot. So this is a Markov chain. The usual graph for Markov chain. This is my little x here times 0. Alright. So this is the first time I hit the little x again. So jump down here. The first time I hit x, right? time, T2x, like this, and similarly, this is T3x. Alright. So the difference between these here, so this will be considered as a tau 1, this is a tau 2, this is a tau 3. Okay? Of course, here we have well, pretty much here we have a discrete case. So the tau in this Markov chain here is a discrete positive random variable, a non-negative random variable, I would say, for safety here. So I think we never really discussed this, but the fact is, then indeed the tau k, all right, inter-arrival times are actually IID, distributed as the Tx. Right. Not really difficult to prove it. Not really difficult. The proof is basically relies on the Stromer property. I hope you guys still remember. So if I condition on the Tx here, then the tau 2 is basically the first time I return to x, which is the same as the tau 1. So the proof here is not really difficult. So I will leave that as an exercise. Alright. Okay, anyway, so as a consequence, the n, and so here I have a continuous, sorry, I have a discrete time, so n sub little n of x, recalling this is the number of times visiting little x up to time n, right? So apparently this is a renewal process. This is simply the maximum on well, I guess you want to call on k of tk of x is less than n. Of course, tk of x can be rewritten as a sum of the tau, obviously. So tkx is simply a summation of I from 1 to k of the tau so hence I can call indeed the number of times visiting x up to the time n is a renewal process. T. Let me put a remark here just in case, a remark which is actually pretty important. A remark that in general, a renewal process and T doesn't really have stationary independent increment, right? And this is a little bit different from the particular case of the Poisson process. So recalling the Poisson process has an independent stationary increment. Let me pressure here. So note that what NT here, right, has stationary independent increment. Namely, that means satisfies that so NT plus S minus NS has a distribution depending only on the difference between two terms. So the difference in level T. And I have an independent increment, then the net n sub Tn, n sub Tn minus 1, n sub T2 minus n sub T1, and n T1 are independent for Tn greater than T1, right? That is the meaning of stationary, which means the distribution here only depends on the difference between the two times, and the independent increment means these random variables are all independent. This is only specific for the Poisson process, but in general, for a new process, it doesn't have to satisfy such a property. Even though it seems to be very tempting, it seems to be very intuitive that it should, but no. The answer is no. All right. And even in this situation here, you're not going to have that property. I don't think so. But anyway, so this is something to keep in mind. So the next thing is a theorem concerning the asymptotic behavior of this process. So recall, sorry, not recall, so with probability 1, the following hold, n sub T over T is going to 1 over the expected value of tau. Right? In other words, well, I guess that means the probability of this event here is 1. So this seems to be okay. So maybe just before I talk about the proof, let me recall a property back in the chapter 1 about the number of times visiting Lilith, right? To give a to illustrate that everything is still consistent. So let me put a remark here. Recall in chapter 1, what do we have? If you have I believe irreducible plus recurrence will imply n sub n x over n will go to
under the stationary distribution.
You're not guaranteed a stationary.
Alright, so 1 over the expected value of
that was a theorem back in chapter 1. So, what is the difference here? So, on the other hand, according to this theorem, alright, so this theorem here does not require anything about irreducibility or recurrence for a Markov chain. So, however, in view of theorem 2, applying in view of theorem 2, we have n sub x over n indeed converging to dx dx. Right. So what is the difference now? What is the difference? Can you swap the difference? So this theorem here doesn't even need irreducibility or recurrence, whatever. You don't need that. You still have that limit. But however, back in chapter 1, we do need these two properties. So what is the difference? The difference is
They hold, right?
right?
The properties actually hold in this place, right?
The same thing, probability 1. Go for probability 1, sure. That's one. Probability 1. The difference is the little x here. So in this theorem, you can start from anywhere. You can start from anywhere in the whole state space. In the long run, the number of times you visit x divided by n, you have to convert to this. But here, the condition is I have to start from little x. Yeah. So in other words, suppose to start from say from a z, another z for instance. Then I'm not. Then the theorem doesn't say I'm going to convert to this. So here, so from for x naught being n z, so arbitrarily z inside the state space. All right, we do have that theorem. However, provided in theorem 2, provided x naught being a real x, then this holds regardless of irreducibility and recurrence. All right. Okay. Yeah. You see the difference? All right. So anyway, now let me go back to the proof here. Let me go back. So now, returning to the proof of theorem 2. So step number 1 is a plane. Step 1 is a plane. I have n sub t. You have to convert to infinity. You have to go to infinity. As t goes to infinity. Now why is that? Why is that the case? Right, so the first thing is we observe nt is an increasing sequence. So we observe that if t1, let's say t1 is less than t2, then nt1 is supposed to be less than or equal to t2. This is clear because if I have a smaller time interval, then I should expect to have a smaller density. Right, so this is say t and t1. This is t time, then I would need, or I should have smaller number of guests. Alright, so that is one piece. And so if you have an increasing sequence, then you need to have a limit, where the limit could be finite or infinite. Right? So that the limit n sub t as t going to infinity divided by a n sub infinity exists, which may be say finite or infinite. We don't know that yet, but at least it must go to something, right? it must go to something. Could be finite, could be infinite. So now the claim is this limit here must be infinite. It has to be infinite. It cannot be a finite number. Right? So it remains to show the probability of this limit being infinity is 1. Alright, so it remains to show this that I'm done with step number 1. So indeed, observe I have probability and infinity less than a little bit. Basically, I try to show that event occurs with, I guess, with probability 0. Alright. So what do I, okay, suppose this limit number here is a finite number, let's say less than a little a. Right? So for, so what is it? So this is the same, let's say, if this is for all t, s of t less than 1. Right? Because I have an increasing sequence. And if the limit is less than n, that is the same as every term in the sequence is divisible by n. Right? No? This doesn't imply that, because n infinity is bigger than every nt. So if n, okay, maybe let me do it. N infinity less than n, alright? Together with the fact that nt is less than n infinity, obviously, because I am increasing up, so my limit will have to be bigger than everything. So that event is a subset of the event for t and t less than n, right? Right, so you have, okay, n1 less than n2, for instance. So you have less than infinite. Okay, so that is one direction. How do I get the other direction? If I have everyone is less than n, the limit is obviously has to be less than n. That is calculus. Yeah. And so we do have the reverse way. And as a whole, those two events are the same. All right. Okay. Okay. Anyways, what do I have so far? I have this event is the same as this event. But if the number of the guests is less than n, up to time t is always less than n, that means, what does it mean? So think about it, like I have, suppose a fixed time t over here. I have the number of the guests started below by n, that means this is one way it can happen. So this, I have tn here, and plus 1, that's one way it can say Tn minus 1, and this is Tn, and then Tn plus 1. Right? That is not an option. Or it could have this. Tn plus 1, Tn plus 2. This is correct. So this is okay. It is part of that event. This is okay. But how about this? Is that part of that event? The number of the guests is valuable by n. This is wrong. This does not satisfy this inequality. Because I have, in this situation, nt now is n plus 1, which is greater than n. So this is wrong. Right? This is part of that, it's not a subset of this event over here. So what does it tell me? It tells me that, tells me that okay, let me keep going. So the probability for t and t less than n implies for all t so n plus 1 is greater than t. Yeah, just like the Poisson process. If the number of guests is valuable by n, that means the n plus 1 guest has to arrive at the time t. Right? So what is this? Right? So for all t, this is this. So this is the same if the n plus 1 guest arriving at the time t for all t, that is the same as this arrival time is actually infinite. Because it is bigger than anything, so it has to be infinite. However, when you look back, what is Tn plus 1? According to my definition, this is the same as some, let me write tau 1 plus tau 2 plus tau n plus 1 being infinite. Is that possible? Is that a possible event with positive chance? It can't be. This is because since we already have tau k belongs to 0 to infinity, excluding infinity. And so I have a finite sum of finite number. And so it cannot be infinite. If I have an infinite sum, then it could be infinite, probably. But here, I have a finite sum. So this is finite sum of finite number. All right? Finite sum, finite number. And so the probability is infinite, has to be 0. All right? So I guess since this and summation of tau k from 1 to n plus 1 is a finite sum of finite numbers. All right. So what have I shown? Basically, I show this probability is bounded above by 0, so it has to be 0. Right? So this is 0 for all n. So 1. So what is left to do? Just take n to infinity. So now, n taking n to infinity, I have probability of an infinity being infinite is the limit. Probability of infinity is n and going to infinity. That's what you want. Alright? Alright, so that's step 1. Okay. So that is step 1. So just in other words, the probability of nt going up to infinity, st going to infinity is this event after probability 1. So now step 2. Step 2 is the strong law of large number. So I have what? So strong law of large number. Alright. I have the Tn over n, which is the summation of tau k, k from 1 to n over n. This will convert to expected value of tau 1. Alright, that's n going to infinity. Says the collection tau k and d and non-negative. Alright. So because tau k and d is non-negative, we do have that limit to hold with probability 1. So note that if you have not seen the strong law of large number, then in general, we have to assume further. So in general, what do we have here? So xk I and d, all right, does not imply summation of sk over n going to expected value of sk. We need to assume further. We need to impose. We need a further condition. Okay, we need to assume further condition. For instance, probably you have seen this. Expected value of the absolute value of x1 is finite. Alright? Probably you have seen that. The strong law of large number. Typically, this is the condition that we impose. This is because sk here it could be a taking values, it's just a real random variable. So taking value in R, alright? But here in this particular situation, because of tau k here, they are non-negative, and so the average of them must converge to the limit, to the expected value of tau 1, right? And so now, okay, so what do I have so far? I have Tn over that, you can see that, right? So now, next here, so I observe, observe that, what do I have? T, all right, this is bounded below by T, so T, and above by T plus 1. this is clear, right? And this is T here. So the last arrival before time T is this time, and the next one has to be after T. Right? The last arrival, the arrival of the NT guest has to be before T, and T is before this arrival time. And so now you divide by NT. Of course you divide by NT. Get the same inequality. Still the same direction of inequality, of course. And so what do you have here? You have so by the strong law of large number over there, because NT going to infinity from step 1, so this ratio going to expected value of tau 1, right? As T going to infinity. That is clear. This can be written as plus 1 times NT plus 1 over NT. Okay. And so this ratio also goes to expected value of tau 1. And this ratio is going to 1. Why is that? Why is going to 1?
Because NT goes to infinity.
Because NT going to infinity. That is the key word. That is actually the key property. You're going to need NT to go to infinity. Otherwise, this may have a finite limit, less than 1. Alright? So the step 1 is actually crucial. It's crucial. Alright? All thanks to step 1. And T does go to infinity, right? Yeah. So anyway, what do I have now? I have this ratio is trapped between these two. Well, I mean, it's trapped between these two limits, which are the same. And so, conclusion, right? I guess it's step 3 for the sake of completeness. Conclusion is. So flip, right? So flip NT over T, we'll have to go to flip, and it will give me 1 over expected value of tau 1. Alright? Yeah. Okay. So I guess I wanted to discuss no, not yet. Not yet. Okay, okay. So I need to have the next part. Okay. So now let me talk about the reward process. So as a program, we have currently two theorem, right? This is theorem 3.3, I believe. Right, so that is theorem 3.1 in your textbook. This is theorem 3.3. I have suppose I have this collection of variant random variables, so Rk and tau k. Alright. A IID bivariant random variables, okay, where assuming what? Assuming of course assuming expected value of the Rk be infinite, and of course here Rk case is a real random variable. And first assuming tau k here is taking values in. Alright, so think about the RK being the reward, or like the outcome for each arrival time. Right? You know, the RT to be the sum of, as usual, NT, K from 1 of the RK. So think about this as being kind of like a reward. Total reward. Total reward up to time t. Alright? Then with probability 1, I have RT over T is going to the expected value of the RK. So R1 over expected value of tau. Right, as T going to. So maybe before I talk about the proof here, maybe for next time, let me just mention the exercise here. Let me mention the exercise, problem number 1. So I have basically here I am repairing a machine. Right? So the time to completely repair the machine is an exponential. However, the mistake does occur with just basically another exponential value, right? And so I'm asking how often our job completed. Like basically it's kind of like this. Basically kind of like that theorem over here. And so I will come back to this next time. For now, just let me briefly mention this. Practice problem number 1. Alright, so think about the time to complete a job. Completely, like finish repairing is, I'm gonna call it to be a, say an XK, X1. Time to complete repairing. And however, a mistake does occur. So, say Y1 time for a mistake to occur. Alright? And so basically the time to, so if I want my tau 1 being the minimum of X1 and Y1, this is the time to finish a job. Alright? That means that either which one goes first. Either I complete the repairing or the mistake will occur. Alright? And so either way I have to stop and move on to a new machine. I have to stop and move on to a new job. And so the time to finish a job is simply the minimum between these two random variables. And this is exponential mu, and this is exponential lambda. Alright? So now it's the time one is basically time to finish a job. Let's say the job number one would be job one. Okay, and so they want to count how many times I actually complete the repairing. Okay, and so RK. So now I have basically RK now, which is summation of 19. Okay, for one, I'm going to count. Indicate a function where the xk is indeed less than the yk. Right? I complete the job, meaning the x1 here has to occur, has to be less than the yk. Right?
I don't see what does lowercase r are not.
Oh, sorry about that. This is RT. My bad. RT. Alright, so and indeed, so well the RK is the indicator function. SK less than YK. Right? So this is the number of times. Complete job. Up to time two. Alright, I guess I should stop here. But continue. We will continue. So I go home, think about it.